Yes.
Okay, so our second speaker of the afternoon will be Paul Seidel. So please.
Yeah, thank you very much for inviting me. This talk will have many shortcomings. Some of them are due to this kind of disembodied nature. As you know, the United States love to go to war, and one of the wars that it has is the war against autumn, which is conducted by means of very loud diesel-powered leaf blowers. So at some point I may have to move to the basement or something. All right, I actually I will try to keep my talk. Sorry, there's no video. I don't think anybody will learn any math from staring at my head for an hour. Okay. And can you not make me administrator for this? Because every time somebody gets in or out, I get notifications on my screen. All right. So I'll try to keep my talk actually quite similar to Umut's talk. So there's a picture of mirror symmetry. It's a picture of mirror symmetry. That probably goes back to the very early days, but was formulated in a particularly clear way by Oru. I will stretch the given formulation a little bit. So let me start with the symplectic side. But even though I'm going to use symplectic geometry, I will do the same thing that Umut did, which is that I will formulate things in algebra geometric terms. So we start with a smooth trajective variety. And an anticanonical divisor. I actually want to make some assumptions here, okay, which is so this divisor should have simple normal crossings with multiplicity 1. So these di's are smooth and in general position. And being a bit of a chicken, I will also say that if A in here is represented by a rational curve, then I want it to have non-negative intersection numbers with each component. Okay, so this is the picture. And I need, so on the symplectic side, I will need a little bit more notation. Okay, so let lambda bar be the Novikov ring of M bar, which is a completion. So it's a completion of the group ring, just based on the second homology group. And so here, every homology class gives rise to a generator, and the generators are multiplicative. And so I will write the generators as Q to the A. Okay, and it's a particular completion, and lambda, this is the same for M. So based on the homology of M, instead of M bar, and with there's an obvious map, right, induced by the homology of M maps the homology of M bar. Is everybody good so far? So in the interest of preserving my concentration, I will not keep a chat window open. So if there are questions in the chat, then I think somebody, presumably the session chair, should read them, stop me and read them out to me. I think that's the best way.
Yeah, that's no problem. I can do that for you.
Thank you. All right. So so what is the most simple way that I could say what the mirror symmetry is, right? So the so the algebraic geometry side of mirror symmetry would be like this: that you have a smooth variety X over this one here with functions. Say W1, Wm. Okay, they're slightly so defined over this slightly bigger. So the definition of the variety only depends on the homology. It's a sort of formal family of varieties that depends on the homology of M, but in order to define the functions, and this, you have to enlarge the coefficient ring. And so if you add up all those functions here, is the what's usually known as the mirror superpotential. Okay, and that is, you know, your familiar picture. If you look at the mirror of, say, projective space, that with respect to the you know, to the symplectic side, you take projective space with the usual toric anticanonical divisor. Then the mirror superpotential has one term for each irreducible component of that anticanonical divisor. Okay. Now there are a couple of issues with this picture here. So one is, you know, if I start with a general, you know, projective variety and anticanonical divisor, there's really no way to construct this X. It usually requires some additional geometric structure, and then the outcome may depend on which geometric structure you can. And the second picture, which is slightly more serious, is the second problem strategy more serious, is that this picture is just wrong. So at the very least, just in terms of you're looking at dependence on the parameters and the Novikov parameters, at the very least, you have to enlarge the picture of what you mean by algebraic geometry to include, you know, not just varieties, but, you know, formal non-commutative deformations of varieties and formal deformations where the structure sheaf OX becomes some sort of germ, right? So, and you know, it's not really clear if I really wanted to make this a general picture, whether even with those enlargements, there is actually a meaningful X. So the you know, so homological mirror symmetry. So the homological mirror conjecture you can read in two different ways. You know, one way you could say, well, we already have some construction of what we need in the mirror, in this case, X and these functions. And then a homological mirror symmetry makes additional predictions about how these are related to the symplectic geometry of the original M. That's certainly one way to do it, but my preferred way is to read the conjecture in a completely different way, which is to say, you don't actually need to construct X or you know, any of the mirrors in a normal algebra geometric sense. Everything should be interpreted in terms of non-commutative geometry, and then it becomes intrinsic to the original M itself. So this picture here on the algebraic geometry side is really just to guide the intuition in that sense. And this is what I will, you know, the way that I will understand this. Okay, so allows us to interpret geometric features of X and W1, Wm in a way that's intrinsic to the symplectic geometry situation. Okay, so in the, you know, most familiar terms here is if I have, you know, don't look at X, but I look at its category of coherent sheaves, I'm going to be you know, a little non-specific about the subscripts for what exactly kind of derived categories we have. Okay, so so there is something that's similar to this symplectic homology that Ullmann introduced, the so-called Bragg-Kaya category. Over lambda. Okay. And oh, by the way, I should say everything in this talk is a little bit shaky in the conjectural side, right? So you can say that I should have introduced some other, questions about the symplectic form and non-negativity and so on and so on. I'm just trying to keep the amount of stuff preliminaries as small as possible. So if you, I would not like you to say that the original smooth projective variety was Fano. That seems a little bit sad, but there would be some assumptions in order to define these things like the Bragg category. But okay, so that now the next thing, more importantly, we had these functions here. Okay, so so these were functions here, well, over-defined over lambda bar. Okay, so maybe I should just do it like this. Okay, so you can think of this thing here as being parts of the zeroth Hochschild cohomology of X. I like to write Hochschild cohomology like this. Okay, and so this one here should be related to the Hochschild cohomology of the wrapped Kaya category. And so correspondingly, we expect to have classes here, which I call Bormann-Sheraton classes. Okay, so these are thought of, and then you can add them up to get something which corresponds to the mirror superpotential. Now, however, when you go into non-commutative geometry, there are always slight surprises. So, usually when you have a function, you can consider its fibers, so you set that function equals to a constant. But generally speaking, if I have an element of degree 0 Hochschild cohomology, then there is no way to associate to it something which you would think of as the fiber. So this is sort of a typical problem. Whether that problem, how relevant the problem is in examples depends a bit on the setup, but I think it's important enough in principle. So I can give you, I can give you a flavor of what so definition. Okay, so let A be, since I'm really working with categories, but I would like to let me make my life a little bit simpler, or say differential graded algebra. If you don't like A-infinity algebras, okay? And so it's Hochschild complex, the complex that underlies Hochschild cohomology. Okay, so this has a bunch of structures, and at the moment, what I need is just the differential, which I will confusingly call delta. And there's also a bracket. Okay. Which is of degree -1. So a non-commutative function is a solution theta equals t theta 1 plus t squared theta 2 plus t cubed theta 3 and so on of the Marokatan equation. Oops. So the Marokatan equation is delta theta plus half theta theta equals 0. When you spell this out, where t is a formal variable of degree 2. Okay, so concretely, when you spell this out, so you have the first order term is a Hochschild cochain, because here only the linear part of the Marraketan equation contributes at first order. And then you have a correction term. See, in commutative geometry, this never happens because on Hochschild cohomology, yes, you do have the Schouten bracket, but the Schouten bracket of two functions is always 0. So, and so on and so on. So there's an infinite sequence. Sorry, this should be -2. Okay, the bracket is degree -1, so θ1 bracket θ1 is of degree -1, and you want it to be 0 on cohomology, and you want to have this thing. Okay, and why is this a notion of non-commutative, successful notion of non-commutative function? Due to this lemma. Okay, so take A to be an A-infinity algebra and theta a non-commutative function. Okay. Let's say that this is over, well, in my application, maybe over some field, some lambda, but let me just do it over the complex number for simplicity. Then there is a quasi-isomorphic pair. Here, where A tilde is an A-infinity algebra over C bracket T. So it's actually, it's linear over a polynomial ring, and θ1 is equals T, and all higher order terms. Higher order terms are 0. Okay. So this is what you would really want, which is that if you have an A-infinity, if you have a space with a function, that makes the space linear over a polynomial ring in one variable. And so that you can take fibers. And so the natural way to do this here is this notion of non-commutative function. Once you have an A-infinity algebra over CT, of course, you can take its fibers. So, so the consequence of this discussion is that we need to upgrade the Borman-Sheridan classes to a collection of non-commutative functions. Okay. Now, in this case here, this is actually, so not just that each single one needs to be a non-commutative function, but it needs to be a non-commutative multivariable function, which is, a solution of the Marraketan equation with several formal commuting variables of degree 2. As I said, the practical importance of this is can vary. In this particular case here, I don't think the upgrade sort of comes for free in terms of obstruction theory, just through various grading accidents in degree, which but there are certainly other situations where that would not be the case, and this is sort of a typical feature. Now, let's say it like this, right? So now, what we want is, I don't want to construct, you could say, well, now you construct it, instead of giving me a mirror, which is an algebraic variety and a function, a collection of functions, you gave me this strange mirror, which is, an A-infinity category together with a collection of non-commutative functions. So, but the point is that you can actually look at the geometry of this as long as you interpret it appropriately. So, formulate expectations about the geometry of the mirror. In intrinsic terms. Okay, so what does this mean? Okay, so for instance, it's a sort of expectation in mirror symmetry that so if you have, if the divisor has just one component and it's smooth, then then the mirror superpotential should be proper. Okay, so if you have a concrete construction of mirrors, you can test this hypothesis, meaning you can say, okay, for me that is exactly what happens. But of course, that will not imply that somebody else's construction of mirror has the same property. So, but there is an intrinsic way of saying this, which is that you should say if it's smooth, then this Vragfakaya category is proper over C bracket T, right? So you convert it to A infinity, you use this lemma above to convert it to an A infinity category over C bracket T, and then as such, it should be proper. And so now this is a reasonable general conjecture. If you ask the specialist, I asked Ben Pomigliano, and he says it's not a problem, he can prove it. But as far as I know, it's not actually in the literature. So this is a way that, you can see that we can actually study the geometry of what one could call the mirror without actually leaving the symplectic geometry side. And there's actually a lot more things that you can do. Let me do something genuinely scary. Okay. So, so suppose the quantum cohomology of your original variety could be semi-simple. Well, that would probably mean generically semi-simple, which means that's an open subset of spec lambda bar. But let me not be too specific here, right? And you could say, well, it's maybe an expectation that this being semi-simple implies that the mirror superpotential has only non-degenerate singularities. Okay. Now, how would I interpret it in terms of homological mirror symmetry, right? So you have, this seems like a tough cookie to attend, but it's, you could say, well, the deformation so you have your non-commutative function, okay, and you can, so to your function is a solution of the Maurer-Cattan equation, so it describes a formal deformation of your category, which and you could say, okay, so this has a semi-simple generic fiber. Don't take me too seriously on this. This seems like a very hazardous conjecture. It essentially banks on a certain interpretation of what it means to have non-degenerate singularities in non-commutative geometry. And this is a very doubtful thing, okay? But what I'm trying to say is that these things like, when does a mirror supposed to have certain properties and so on, can be studied within non-commutative geometry, as long as you can figure out what the correct non-commutative geometry analog is of these properties. Okay, are there any questions? All right, so the main question that I would like to talk about here.
Well, I had a quick question, sorry.
Yeah.
Should it be, I'm getting confused, is it the Ratsky category of X in what you just wrote, or what was your notation?
Okay, X is the mirror which doesn't actually exist, right?
Yeah.
Oh, sorry, my notation is not the same as Umut's notation. So my notation is that M bar is a smooth projective variety, and M is when you take out the anti-canonical divisor, and X is the stuff that happens on the mirror, which will never actually be used.
Yeah, okay.
Does that help?
Yeah, I got it actually. Sorry, thanks.
Okay. So, all right. So the main thing, so an important question here is the dependence on the Novikov parameters. So lambda or lambda bar, right? What's interesting is the following thing is that so you have this picture here where you have so in the classical mirror symmetry picture. Okay, so you have this one here, and you get X and W, which is, and these are defined over lambda bar, so it's, you can think of it as sort of a family over spec of lambda. It's a horrible thing to say. I know algebra geometrically not exactly correct because of the properties of lambda bar. But so so when you look at this, okay, so it's a family. So there's obviously two things that make up this geometric object. One is X and the other is W, okay? And so there should be, so in a spec, say, you can ask yourself, okay, so in spec, say lambda bar, or more precisely spec lambda, there should be a foliation along which X does not actually change. But W changes. Okay. So so moreover, if you change the, let me talk in informal language here. If you think of this lambda as formal Kähler parameters, if you change the Kähler parameters, it could be that X changes, or it could be that X stays the same, but W changes, right? Now you might say, well, in my simplest example that I have in mind, like mirrors of projective space, X is an affine variety. So from the point of view of formal deformation theory, it can't change at all, but that's not correct because we include these generalized deformations. So, an affine variety can have plenty of deformations given at first order by vector fields. Deformations to a non-commutative variety. So the question, and this goes back to papers of Orul, Katsarkov, and Orlov, is when do you exactly how do the given parameters that I have on the symplectic side distribute themselves over the mirror sides into changes of symplectic structures? Okay, so what can I say about this? Okay, and what I can say about this is a bit tentative, especially in this particular context here. Okay, so all right. So what I need to say is that, let's go back to this Novikov field. So for Z in H2 of M bar lambda bar, there is an associated derivation of lambda bar, namely, okay, so dz. So if you have some exponent here, you take this z is a two-dimensional homology class, you pair it with this homology class. Okay. So I want to look at, so this is sort of a vector field on your space of Kähler parameters. Okay, so I want to look at particular z's, which is that the following thing. So at genus 0, 1 point Gromov-Witten invariance. Okay, which is so for A in H2 of M bar, this gives me a cohomology class, which is the cycles spanned by these rational curves, which is of degree 4 minus 2C1 of M bar dot A. What am I trying to say here? Okay. It's maybe rational, but let's say complex. And I want to look at actually those where this first Chern class dot A is actually equals to 1. So organize them into say Z upper 1. Okay, so this is the sum over all ZA Q to the A. This will be an element of H2 M bar and the bar. And I sum over all those A such that, let's say, it intersects this divisor with multiplicity 1 and intersects the other divisors not at all, not at all, J not equals to I, okay? Remember, the sum of the DI is the anti-canonical divisor, so we're good, okay? All right, so I'm associated to these, so associated to so there's one of them for every irreducible components are derivations, okay, which I would just call D1, dm, just to shorten the notation of lambda bar. Okay. So okay. Maybe I should call those, we can do the same. Well, I'll just not do this. Okay. All right. So now I will make an assumption which is very unpleasant, and I would really like to avoid this, but I will discuss this in just a second. So suppose that this anti-canonical divisor is the fiber, because it includes almost all examples that you had in mind of a fibration M bar to P1. So it's just like a rational elliptic surface, and so the anti-canonical divisor is the fiber. So then is a constant in direction of Z1, 1, ZM1. Okay. So this is actually incomprehensible statement a priori. So what does it mean to be a constant in the direction of these? Sorry, I should maybe say in the direction of D1 up to Dm. Okay. Here I've extended coefficients to lambda bar. So what does it mean to be constant? So more precisely, constant in direction. So it doesn't change, right? But you have to interpret it slightly more correctly. So it means that there is a flat categorical connection over these derivations. Means it doesn't change. Okay. So let me see. So what is the definition here of this horrible notion? Okay. So let's do for a single derivation. So suppose A is an A infinity algebra over, maybe I should say a flat A infinity connection, we call it this. Okay, suppose that this is an A infinity algebra over some ring R, and D is a derivation. And I want to say that this derivation can be lifted to some sort of like a connection, something that infinitesimally pushes A around in the direction of this derivation. Okay, so so an A infinity connection over D consists of, well, you might say, okay, so you might think of, well, it's a connection, so it's probably like a linear endomorphism here, which satisfies, so here's F is in R, which satisfy the usual connection property with respect to this derivation. And should be compatible with all the A infinity operations, but you know that is way too much to ask. They don't typically exist. So what actually happens is that this comes with something of degree 1 and 2, a bilinear map of degree -1. Okay, and these here are these terms here, all the terms about except this one here are linear. Are linear. And satisfying a super equation that I will not write down. Okay, so yes, so that is sort of you know, of course, in ordinary geometry, you can integrate connections. That is a separate story. That you know, it needs some kind of, maybe you can formally integrate. That gives me this this picture. So this would be for one derivation. So if I have constant in the direction of several derivations, I need a sort of multivariable connection, and there is a notion of flatness of those, just like notion of flatness of an ordinary connection. Okay, and this is what I want, and so that would give me the idea. Let me draw a small picture here somewhere. Okay, so you have, this is spec lambda bar. Okay, and so it's, you know, and so you have these, you have a sort of foliation along which the Vratikai category remains infinitesimally constant. So in directions tangent to this foliation, the category should not actually change, which corresponds to the mirror not actually changing. So the mirror not actually being deformed. Okay. And so the idea is that this foliation is exactly the foliation that's given by these vector fields d1 up to dm. Okay. Now you could say, well, what is it? So basically, the Gromov-Witten invariance for curves that intersect your divisor once, and since there's several components, I can pick which components they intersect, would give you directions along which the Vratikai category does not deform. Why is this condition, you know, that it's a fiber of a fibration? That's a very unpleasant condition. The fact is that, you know, in order obviously to have, you know, tangent spaces to a foliation, right, you need to have some sort of integrability condition, which means that these these derivations, had better commute. And generally speaking, I don't think they commute. So I probably have, there are some terms that involve the restriction of the first Chern class of M bar to the components of your divisor. Obviously, it's a fiber of a fibration, then the first Chern class is represented by any fiber of that fibration, and therefore it restricts to 0 on the infinity, and I do not have that problem. What this probably means is that I have the wrong formula for these things in general. So instead of just using these very simple Gromov-Witten invariants, I should probably be smarter, but smartness is failing me. as of recent. The good news is that note proved for D infinity a smooth fiber. So occasionally, even in symplectic geometry, I think we should have a theorem. So this is actually no when it's a fiber and when it is actually smooth. And you could take that proof as a model for the general case. Okay. Are there any questions?
Do you have any idea how this works for log Calabi-Yau surfaces?
Do I have an idea for how this works for log Calabi-Yau surfaces? Meaning what?
Well, you know, we had a construction using the scattering diagram, myself with Mark Gross and Sean Keel, where we got a mirror family that was defined over a base that depended on the Picard group of the compact guy, M bar.
Yeah, yes, that's what we have. Yes, yes.
Yeah, and then there was a sort of so that was like the torus associated to the Picard group of M bar.
Which
and then
it
there was
is.
a sort of subtorus that acted. We called it the relative torus.
Yeah, yeah.
That was
Paul,
associated.
Paul Hacking. I think that foliation there is your relative torus.
Yeah, but I
just wondered. Yeah, I couldn't sort of match it up, but
yeah, neither could I.
Yeah, well, I'm glad. That probably means that I'm somehow wrong. But yes, so as far as the original Picard torus is concerned, you know, spec of the Novikov ring is just a formal completion of that. So there,
Right.
I'm not worried. I do not see that the foliation is something simple like, you know, a linear subtorus. I mean, is your subtorus a linear subtorus?
Yeah, so it would just correspond to the cohomology class of the DIs.
Yeah, that you know,
there's also a simplification that happens in dimension 2, which is kind of like what happens for K-free surfaces, that somehow, you know, there's no sort of quantum corrections to the mirror map or something, which makes it simpler.
Yeah.
And probably what I'm saying is, you know, your situation probably becomes simpler in that dimension, but not.
Okay, yeah, fair enough. So what you're saying is that, you know, under suitable assumptions, there would be no such Gromov-Witten invariance.
No.
And
But even in dimension 2, those Gromov-Witten invariants are there.
Well, but the Gromov-Witten invariants that intersect the divisor with multiplicity 1, right? So I mean, certainly the curves, you could have curves that are components of the divisor that might satisfy those. And that would explain the appearance of this class as DI.
Also, the Gromov-Witten invariants you wrote down, they're reminiscent of this construction of the scattering diagram.
Yes, they are, yes.
I wondered if you had any comment about that.
I don't have any comment about that, but I think that you know, the first question is something I clearly need to think about under what circumstances, you know, these classes here, you know, reduced to something stupid. But I think the problem is that your assumption and my assumption that it's the fiber of a fibration, you know, leave very little room in common. But what I can say is that for a rational elliptic surface, if I put a smooth fiber at infinity, which is not what you call, I think, a relative Calabi-Yau, these invariants, of course, highly non-trivial.
Right.
And so in that case, the foliation is nothing like, you know, a stupid subtorus.
Thanks.
But on the other hand, you know, look, when you one thing that I should say in warning, so you construct the mirror. Okay, let me say this makes maybe more sense. When you construct the mirror, you know, so you construct it over some kind of torus, but is it clear that this is the same parametrization of the torus as that's given by Kähler variables, by Kähler moduli?
Well, it should be canonical coordinates.
It should be canonical coordinates, which are these coordinates. Okay, yeah. Well,
That's right,
then,
yeah.
yeah. So then, I don't know. Generally speaking, for this example, like rational elliptic surface and d infinity being smooth, it is definitely not like a flat subtorus. I would, to the best of my understanding, at least, which may not be as great. Okay. All right. So
maybe,
yes.
Apologies. Like in the setup of Paul Hacking was asking when he's looking at local labial surfaces only, like if you blow up k points in P2, then you can extend each of the theta functions that appears in the scattering constructions we have to a conic vibration, by which I mean you would have fibers which consist of two P1s meeting, like, and you would just have these conic fibers, like k+1 conic fibers, your maps would be, and usually our anti-canonical divisor we fix does not agree with that. So I don't think your setup agrees with our setup. I mean, you have this assumption, the infinity being a fiber, but we, like in the setup of the pizza surfaces, your theta functions are P1 vibrations where you're seeing the fibers are conics, and the infinity is usually different in our setup. So I don't think it connects directly, as far as I understand.
I'm sorry.
I mean, the assumption Paul has that the infinity is the vibration, I mean, the anti-canonical divisor is a vibration. I don't think it connects directly to the local labial setup Paul Hacking was asking. I don't see that.
That's true, yeah.
Yeah, it's different.
So do you have a suggestion for what I should put in the general case instead of, so it should be something which in some cases reduces to what I'm saying with Gromov-Witten theory, and in other cases it reduces to just the classes of the DI.
Yeah, I need to think about that, yeah.
Okay, all right. So the, okay, let me say we're getting sort of further and further ahead as things become more and more dangerous. But let me say what the next issue would be, right? So once we have an A infinity connection over some derivation of this parameter space, we have an induced connection in the ordinary sense on the partial cohomology, in this case here, of the wrapped category. Okay, so we can ask about the derivative of the Bullman-Sheridan classes. Okay, meaning what? Well, once you have a direction where, informally speaking, the mirror does not change, right? So you deform in that direction in the Kähler parameter space. The mirror does not change, but the function changes. Functions change, but of course, the functions change in a space that's, a linear space and in fact a ring. Okay, and so you can ask, what, is there a formula for how it changes? Because you really want to, recover the linear structure that you're interested in on the mirror. So this is the last thing I'm going to say. Okay. This is very strong assumption. So suppose d infinity is the fiber of a vibration and is smooth. So m equals 1. Okay, so take what I called d, just before that I called it d1, and the induced connection. the Hochschild cohomology of the spread category. So now we have, we have a fibration with anticanonical fibers that work in the complement of one such fiber. Okay, so for S, so this is the Borman-Sheridan class. Okay, let me write the induced connection again as this. Okay, so for this the Borman-Sheridan class, and I try to differentiate it. Okay, and it's almost S squared. So this uses the ring structure. And there is a wrong sign that I put in. Okay, minus some multiple of the unit. So this is the unit in corresponding to the function 1. Okay, and this is very strange formula. Okay, where Z2 in lambda bar counts rational curves with C1 of M bar times a curve equals 2 through, sorry, I'm trying not to start a new page here, through a generic point. Okay, so this is the next theory. Remember, I only used Gromov-Witten invariants which intersect the anticanonical divisor once. Now come the ones that intersect the anticanonical divisor twice. And if I take a one-pointed Gromov-Witten invariant, well, it lands in H upper 0 of the manifold, meaning there's some number of them going through a generic point. And this is the coefficient that shows up here. So this gives you a way of figuring out as you go along the leaves of this foliation, how do you actually your functions change? To be honest, I only did it for this leading order term of the non-commutative function, which is the Borman-Sheridan class. I should maybe say a word about why we as symplectic geometers are maybe interested in this. Okay, which I have not, something that I haven't featured so far. What we often like to do in symplectic geometry is that in addition, I fix an ample divisor. And I work relative to that ample divisor as well, which allows me, just in a formal sense, which allows me to have, inside the Novikov ring, just sort of a non-negative part, which contains a point where the Kähler parameter is formally sort of set to 0, sort of the exact point. And this exact point, we understand everything much better. And so if we have an operator that differentiates in some direction, we can hope to move our insight from the exact point to other points in the Kähler modular space along the leaves of this foliation. And for that to be a way to actually compute these structures, in particular this S and other things that mirror symmetry are interested in. But that is a story for another day. So as far as this theorem is concerned, so this makes a lot of assumptions. I wish that there was, so before that I had a theorem in the same situation and a conjecture, which also had this fibration property, but it dropped the smoothness property. And so you had several Borman-Sheridan classes and several vector fields. Yeah, I wish there was a conjectural version of this theorem, this more general thing. I'm not yet confident exactly how to write down. And if I want to drop this fibration property, I run into the same problem as before, which is that I don't have the correct formula, obviously, for the leaves of this fibration. And that is my talk.
Are there any questions?
Now you can see me.
Anyone online want to interject questions?
There are some excellent pigs behind you.
Thank you.
Hey, Paul, could you share your slides? Because I'm a bit slow. I couldn't really keep up.
Yeah, I would appreciate that too.
Okay, I'm sorry.